As you look up into the night sky, what do you see? Bright stars, distant planets, an all-encompassing static universe?
If you said the latter, think again. Our Milky Way galaxy is only one of the estimated 100 billion galaxies in our universe today. If so, then the question arises, why do neighboring galaxies appear so small to the naked eye? Is the universe so expansive? The answer is yes, and it continues to expand at an accelerating rate, described by Hubble's law of cosmic expansion and Einstein's original equation.
In December of the year 1924, astronomer Edwin Hubble used a telescope to observe distant celestial bodies and discovered the existence of galaxies other than our own. Hubble analyzed them extensively and eventually noticed that the light exhibited by the galaxies was stationed more towards the red end of the spectrum than the blue end, indicating that they were millions of light years away and receding farther.
Hubble's observed redshift is due to the Doppler effect, the shifting of color or frequency. According to the Doppler effect, as something moves toward us, its light is emitted in shorter wavelengths, causing us to perceive the light as blue. In contrast, as something moves away from us, its wavelengths become longer, causing us to perceive the light as red, just as Hubble experienced with neighboring galaxies.
Therefore, the farther celestial bodies appear, the greater their degree of redshift, and the higher the rate of overall cosmic expansion. Hubble's law describes precisely this, with HO being the Hubble constant, d representing the distance to a galaxy, and v equaling the galaxy's recessional velocity.
Thus, we have proved that the universe is in fact expanding. Nevertheless, the question remains as to what accounts for the recession of galaxies from one another. The two known variables include the still debated momentum incited by the Big Bang and a theoretical repulsive force which opposes gravity known as dark energy.
Similar to the way in which fireworks detonate, at the incitement of the Big Bang, matter primarily in the form of light rays and quark plasma immediately began to move away from neighboring particles, and therefore expanded the universe by means of momentum, the product of its velocity and mass. This resulted in a constant kinetic energy, accelerated by the existence of a theoretical repulsive force acting between celestial bodies, causing them to move away from each other, dark energy, which constitutes approximately 68% of the entire universe.
It is important to note that dark energy recession applies only to large-scale celestial bodies, not small-scale galactic matter such as planets or stars.
Albert Einstein was one of the first to predict the existence of dark energy through his original equation, the initial equation which did not consist of a cosmological constant. Furthermore, according to the law of conservation of energy, energy can neither be created nor destroyed, but solely transferred from one medium to another or transformed from one form to another. The existence of dark energy behaves similar to potential energy, and its repulsive property results in the transmission of energy as acceleration. Likewise, an archer draws back their bow and accumulates potential energy, to then release the arrow, which translates the energy into kinetic motion.
Now that we understand Hubble's law, the Doppler effect, kinetic motion, Einstein's original equation, dark energy, the law of conservation of energy, and how each relate to the universe, the real question is, how could it not be expanding? Cosmic expansion is primarily significant because it not only gives us clues as to the beginning of the universe itself, but also allows us to continue observing and learning about its development.
So, next time you look up at the night sky, what will you see?